Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this section now, we'll begin the topic of hypothesis testing, and this chapter is an introduction to this. So, a statistical hypothesis is an assumption about a parameter of the population, and that assumption may or may not be true. So hypothesis testing refers to the formal process that a statistician goes through to accept or reject a statistical hypothesis. Now, statistical significance refers to the likelihood or probability that a statistic derived from a sample represents a genuine phenomenon in the population. In other words, I'm trying to determine if the difference between my sample and the population is too large to have occurred by chance. Now, a little history here. William of Ockham was a Franciscan monk who was born in a small English town in 1280, but he was a very influential philosopher, theologian, professor, and expounded many ideas, including church politics. But he was a fervent advocate of the power of reason, denying the existence of universal truths and espousing a modern philosophy that was quite different from the views of most of the people at the time living in the Middle Age. And he became a founder of what a foundational principle many of us call Occam's razor. So what does he have to do with data mining and statistics? His name has become associated with a very simple idea. He explained it in this way. The simpler explanation is the preferable one. Or more colloquially, keep it simple, stupid. The most simple explanation is often the correct one. Now, any explanation should strive to reduce the number of causes to a bare minimum. This line of reasoning is referred to as Occam's razor, and it's his gift to us as data analysts. The best way, of course, to determine whether a statistical hypothesis is true would be to look at the entire population. But more often than not, that's impractical, and researchers typically have to deal with a sample of the population. If the sample are not consistent with the statistical hypothesis, the hypothesis is going to be rejected. There are two types of statistical hypothesis. There's the null hypothesis, and it's denoted by H0, and it's usually the hypothesis that sample observations result purely from chance. The alternative hypothesis, denoted by H1, is a hypothesis that sample observations are influenced by some non-random cause. Put another way, the null hypothesis is the assumption that any differences among observations in a sample are due simply to chance. The null hypothesis refers to the absence of effect in the population. The alternate hypothesis asserts the exact opposite of the null hypothesis. Let's see if we can make this easy by using an example. Suppose we want to determine whether a coin is fair and balanced. A null hypothesis might be that half the flips would result in heads and half in tails. The alternate hypothesis might be that the number of heads or tails will be very different. So symbolically, these hypotheses would be represented as H0 probability equals 0.5, and the alternate hypothesis would be that the probability is not equal to 0.5. So suppose we flip a coin 50 times, resulting in 40 heads and 10 tails. Given this result, we would be inclined to reject the null hypothesis. We would conclude based on evidence that the coin was probably not fair and balanced. Now, some researchers say that a hypothesis test can only have two outcomes. You accept the null hypothesis or you reject the null hypothesis. But, modern, especially many statisticians, take issue with this simply accepting the null hypothesis. Instead, they say you fail to reject the null hypothesis, meaning I couldn't disprove the null hypothesis was incorrect, but that doesn't prove it is correct either. So this is my version. There is insufficient information to reject the null hypothesis. That's the way I would prefer to say it. So let's take a look at this process. Statisticians use a formal process to determine whether to reject a null hypothesis based on sample data. This process is called hypothesis testing, and it's done in 4 steps. The first is to state the hypothesis. This involves a null or an alternate hypothesis statement. The hypotheses are stated in such a way that are mutually exclusive. In other words, one cannot be true if the other is also true. Next, we're going to formulate an analysis plan. This is going to describe how to use sample data to evaluate the null hypothesis, and it's generally going to focus on a single statistic. Then we're going to analyze our sample data, and that's going to mean we find the mean, the proportion, t-scores, z-scores, etc. And we'll describe how we do this analysis. Then we're going to interpret the results. We're going to apply the decision rule described in the analysis plan. If that value of the statistic is unlikely based on the hypothesis, we would fail to reject the null hypothesis. Now, in hypothesis testing, we may actually be wrong. And there's 2 forms of being wrong when we try to reject the null hypothesis. A type 1 error, that occurs when a researcher fails to reject a null hypothesis when it is in fact true. So the probability of committing a type 1 error is called the significance level, and it's denoted by the alpha symbol. And we'll talk more about why that's important. A type 2 error is the opposite. It occurs when the researcher fails to reject the null hypothesis, but it's actually false. The probability of this is also called beta. The probability of not committing a type 2 error is called the power of the test. So how much difference does there have to be? Assume my population average age of an employee is 35, and on my sample I find the average age is 35.001. Technically, yes, it's different, but is it different enough to be considered meaningful? How different does your sample have to be to indicate that there is something wrong with the sample not reflected in the population? The further away the sample mean is from the population mean, the less likely it is to occur by chance or random sampling. Now we'll have 2 kinds of outcome, common and rare. The common outcome is when the difference between 2 statistics is small enough to be reasonably viewed as a probable outcome under the null hypothesis. A rare outcome is when the difference between the 2 statistics is large enough to be reasonably viewed as a probable outcome under the null hypothesis. Now, before we can reject a null hypothesis, we want to be sure the difference that we're seeing in our sample statistic was not due to just chance. So the accepted, at least in social sciences especially, the accepted convention is to set that level at 5%. In other words, if the probability of the sample mean differing from the population mean is less than 5%, the probability is not likely due to chance, and we would reject the null hypothesis. So using that, we would define our boundaries of the common and rare outcomes. The common values would be within 95%, which is plus or minus 2 standard deviations. So the 5% leaves 2.5% on either side of the curve for a standard distribution. This range enables basically establishing the level of significance. At times, however, we're going to want to do what's referred to as a one-tail test. And that is, instead of taking that 5% and putting it on both sides of the normalized distribution, we put all 5% on one side, like in this case, a shaded area. That falls outside the curve. But bear in mind, you can put the one-tailed test on either side. It could be to the left or right of the distribution. And once again, the two-tailed test takes that 5% and puts 2.5% on each side of the normal distribution. So let's take a working example. Let's assume, or I theorize, that the average age of a female employee is the same as that of the population of employees. So my null hypothesis is that the mean of the sample is equal to the mean of the population. My alternate hypothesis is that the mean of the sample is not equal to the mean of the population. Now, because the sample mean could be greater than or less than the population mean, this means it's going to be a two-tailed test. Now, before we can reject the null hypothesis, we need to make sure that the difference was not due to chance. And the accepted convention is to set that level at 5%. In other words, if the probability of the sample's mean differing from the population mean is less than 5%, the probability is not likely due to chance, and we would reject that null hypothesis. Now, I'm going to use a t-test in this particular example. And the reason I'm choosing the t-test, even though I have a significant sample size, I do not have the entire population, so I do not know the standard deviation of the population. So just to be safe, I'm going to use a t-test. So let's take a look at how I would go about doing this in 9. All right, in my 9 example here, I've used the table creator node, and I've created some sample data. What I've got here is a group. I've got a column called row type, and it has values of females and their ages. And I scroll down farther, I can also get a group that I call the row type of all, which represents the population, and their ages. Now, I'm going to run them through the independent groups t-test node. When I click on here, I can see it's designed to compare the means of observations in the same column between two different groups. So in the configuration, I've told it the column I want to use to group by, which is row type. And then I chose the group. It populates it with all the known groups. So you can choose. In this case, I want to compare between females and all. And I gave it a confidence interval of 95%. Now, when I look at the output of this node, I can see this. The average age of a female is 46.8, and the average male age of the population is 50.49. So there's a difference of about 4 years, a little over 4 years difference between them. I can also see that the standard deviation is not the same, which means the variance is not going to be the same. Now, if I look down here, since the equal variance is not assumed, I can see that the probability of a two-tailed test, the probability of this being due to random chance, is 5.29 to the -6 power, which means this number is well below our 0.05 threshold. So in this case, I can reject the null hypothesis. That's how to perform this t-test within 9. Retaining the null hypothesis is referred to as a weak decision. This doesn't mean the null hypothesis is true. It simply means that common outcome may have been produced by chance. However, rejecting the null hypothesis is a strong decision. The existence of a rare outcome indicates the null hypothesis is likely false. So we have 4 possible outcomes when we're doing hypothesis testing, and we covered this in the introduction. The first is that the null hypothesis is true and it is not rejected. Second would be the null hypothesis is true and it is rejected. That would be a type 1 error, and it's only would have a 5% probability, assuming that's the confidence interval you used. The third is that the null hypothesis is really false and you didn't reject it. That would be a type 2 error. And finally, that the null hypothesis really is false and it is rejected. So basically, number 1 and number 4 are good. Number 2 and number 3 are indications of an error. Let's set out with another example. Let's say that I believe that married people earn more money than single people, and in addition, widowed people earn more money than married people. Let's set out to determine if the data supports this claim. So let's start with a null hypothesis that the salaries are actually the same. And because the independent groups t-test, what that's doing is testing the means to see if they are equal. So I've got some sample data here, very similar to the last one, where I have a row type and the salary amount. So I've got widows' salaries, and I've got married salaries, and I've got single people salaries. Now, I'm going to use this data, but in independent groups t-test, these groups are all independent of one another. There's no relationship between, the rows. So, but this node is going to allow me to test the means of two values at one time. So I'm going to start by comparing widowed to married. And what the independent group t-test is going to do is say, just like you saw in the last example, it's going to take the row type and I'm going to compare married to widowed with a 95% confidence interval. And I'll go ahead and execute that and then open the views. And I can see the widow's average salary is $537 and the married is $185. We'll talk about the Levine test in an upcoming chapter, and we'll explain more about this, but because do I know that the variances are the same or not? This will help us understand that, but we'll talk about that in a upcoming chapter. For right now, however, doesn't matter, equal or variances or unequal variances. In either case, the p-value is still well below the 0.05 threshold, which means the difference between these two means is real. So I can reject the null hypothesis. The means are not the same. So now let's go ahead and do the same thing, except this time I'm comparing married against single with a 95% confidence interval. And when I execute that and open the view, now I have a mean of 185 and 129. They're much closer together. And in fact, again, looking equal variances assumed or not assumed isn't going to matter. I can say that the p-value is 0.07. So that is above our 0.05 threshold. I fail to reject the null hypothesis. I cannot be certain that married people make more than single people. This test does not prove that out. So let's summarize. With hypothesis testing, the null hypothesis is going to be H0 and the alternate hypothesis will be H1. When it comes to outcomes, there are common outcomes and rare outcomes. Rare would be outside the realm of chance. Boundaries, we can do a one-tail test to test the one side of the distribution, or a two-tail test. When we reject the null hypothesis, we have strong decisions and we have weak decisions. And finally, when it comes to outcomes, the idea that the null hypothesis really is true and is rejected is a type 1 error, and that the null hypothesis is false and it is not rejected would be a type 2 error. That completes this chapter of the class. Feel free to move on to the next chapter.